Okay, this is the third and final of our t-tests for the class. This t-test is the one for two related samples. I'm using this generic term, two related samples, because we're actually going to talk about a couple of different kinds of experimental paradigms where you might use this, and you might call it a different kind of t-test, depending on which situation you're using it for. But the important thing that we understand here at the outset is if you have already taken the time to master and really conquer the material of the last two modules, this will be a breeze. If you haven't, then this will be a really good review and a good opportunity for you to kind of work through that material again and learn it a little more deeply. To introduce the repeated measures t-test, I want to talk about the kinds of research designs that will typically be employed when using this statistic. So a repeated measures design is also sometimes called a dependent samples or within subjects or paired samples design. It might also have some other names too, but it's important that you understand what's going on here, not just the names. In these cases, you have two separate scores that are obtained for each individual in the sample. So, you might draw, for instance, a sample of people who received some kind of treatment for a condition. That's the easiest example to understand or to wrap your mind around. Let's say that you're getting therapy, some kind of psychological therapy, and you go in on your first day, you fill out a survey that describes your level of depression, and we'll consider that your pre-test score or your pre-treatment score. And then you go through a few sessions of cognitive behavior therapy, and at the end you take that same inventory a second time, and that tells the clinician what level your depression is at after the therapy is over. The same people participated in the survey both times, and we link together their scores pre and post. So using this figure here, I'll show you that in the first column, these are the pre-test scores, and in the second column are the post-test scores, but the subjects are the same across the row. So this is person A, and they had a pre-treatment depression score of 10 and a post-treatment of 14. Subject B had 15 and 13. Subject C had 12 and 15. So after you obtain those two scores, you subtract the difference. You take the second score minus the first score, and you get a different score. 13 minus 15, negative 2. 15 minus 12 is 3. 12 minus 11 is 1. So you take the post-test minus the pre-test, whatever your research situation is, and you obtain these difference scores. These different scores, we imagine to ourselves, come from some hypothetical population of different scores. And this would be all the people in the whole world who ever have or ever could participate in cognitive behavioral therapy and fill out the depression inventory before they did and after they were done. And we took the difference scores for everybody in that imaginary population. These four would be the sample that's drawn from that hypothetical population. Now, we would never actually do that. You couldn't even possibly treat all the people who ever had depression or needed CBT, and so we would never have this. But we imagine to ourselves, for the sake of the statistic, that these scores came from the hypothetical population of different scores. And we are asking, how big of a difference would this really be if you were able to treat every person in the population? How big would the treatment be? We can estimate how big it is based on these four scores here, but we know that it won't be exactly the same as if you were able to treat every single person in the population. So our goal is to figure out, is this difference here really different from no difference? And if it is different, how different? what score might this actually be if we were able to treat every person in the population. In this research situation, where we're using a repeated measures design, where we're measuring people more than once in a repeated fashion, so we're repeating the measures twice down here, that's why we call it a repeated measures design, then we use the same subjects in both treatment conditions. There's no risk of the participants in each treatment group differing significantly from each other because they're the same people. This is a fantastic benefit to a repeated measures design above and beyond what we learned about in the last module, the independent measures design, where the measures were given are for two independent groups who were not related to each other. In those groups, we recognized that there would be some variability just because the people in the two groups are not the same as each other. Maybe you have Jill and Sally and Bob in the first group, and in the second group you've got Anton and Tony and Bartholomew, and the people in the two groups are not the same, and so just because of pre-existing differences, they're going to be more different from each other than the two groups in this situation are, because group 1 and group 2 are comprised of the exact same people. And when that happens, you are really reducing your what's called error variance. The variability across these scores here that is because of different people being in the first condition versus the second condition. Because in this situation, there aren't different people in the first condition, in the second condition. It's the same person. Subject A is in both. And so you've reduced the variability that's due to just random differences from different people. However, we can do what's called a matched subjects design, where we actually do use two different groups of people, but we pretend like they're the same person. Now, I know that sounds a little bit like cheating, but a matched subjects design approximates the advantages of a repeated measures design, where we're pretending that the individuals in a sample are actually the same people because we've matched them one-to-one with an individual in the other group, in the other sample, on relevant variables. So subject A and subject E are matched together with their score of 10 and 14, and we're pretending that subject A and subject E are actually the same person, even though they're not. And the reason we can get away with doing this is because subject A and subject E will have to have been matched on some relevant characteristics. They're probably the same sex, they're probably about the same age, they're probably about the same education level, and they've probably taken some kind of pretest that assesses their upbringing and pre-existing psychological damage and stuff like that. So when you put them through the therapy, Subject A would not have experienced the therapy, Subject E would have experienced the therapy, but instead of doing a pre-post, you can compare the people who didn't have therapy versus the people who did have therapy, and you treat them as if they're the same person, as long as you've made sure that they're really similar on a lot of variables. Once you do that, then you feel like, even though it's a little bit of a cheat, it's maybe in some research situations it's the best you can do. And so you just say, all right, given that we can't actually give a pre-post here, then we're going to do this approximation, and we're going to match up two people on a bunch of characteristics so that it looks as if they're the same, even though they're not. And then you would do the same thing as you did before. You would compute a different score. You would take 14 minus 10, 13 minus 15, 15 minus 12, and so for every participant, you would compute the different scores, and then you would run your t-test on these different scores from this imaginary population where all the people, this is all the differences of people that are not actually the same, but they're matched up. And anyway, so we would never actually do this, but we just imagine to ourselves this hypothetical population, and we're trying to figure out what is the difference in that hypothetical population if we were to compare people who had received treatment and people who hadn't received treatment. How big of a difference would there be between those two groups? So participants are not identical to their match, but we ensure that the samples are equivalent enough with respect to some specific variables, and so it's close and it's okay. A repeated measures and matched sample design are both examples of this concept we call a related samples design. So you remember on the first slide of this module, the title slide, I had used this phrase, related samples. And the reason why I used it there is because this is kind of a parent category that encompasses both repeated measures designs and matched samples designs. And so you can use the same kind of t-test for either of those two types, and we're calling this t-test a related samples t-test. These two designs use statistically equivalent methods. It doesn't matter whether you've used this one or this one. You're going to use the exact same t-test, but we use different numbers of subjects. A matched sample actually has twice as many subjects in the study as a repeated measures design has. So let's imagine to ourselves that we have a research situation where people undergo a treatment of drinking lemonade. And some of the lemonades have actual sugar in them, and some of them have a sugar substitute like Splenda. I'm using this example because it's based on real research that has found that if you drink lemonade with real sugar in it, then the sugar that's in the lemonade triggers gives your brain the glucose it needs to make effective self-control decisions. So even though it's actually worse for your caloric intake, if you have some sugar in your system, your brain is better equipped to make effective decisions about whether it should refrain from eating a cookie or a brownie. And so I know that sounds odd, but if you drink lemonade with sugar, then you're less likely to make a poor choice about a cookie or a brownie or a bowl of ice cream a few minutes later. So that's the research example that I'm patterning this after, but we might imagine to ourselves that we're comparing people who drank lemonade with sugar compared to those who drink lemonade with Splenda. Now, if you have a matched subjects design, then you are grabbing two groups of people. Each group will have 30 in it, and you're matching up the 30 people 1-to-1 so that person 1 is matched with person 31 in the other group, person 2 is matched with person 32, and so on. So you're matching up the two people in the two groups. I hope that makes sense. You're matching up one person from each group with each other. But you've got 60 people here in the study because you've got 30 people per condition. But in the within subjects design, where you're comparing the same people, when you're making comparisons within the groups, within the subjects, then you actually only need to recruit 30 people because they do both conditions. You first have them drink lemonade with sugar, and then the next day you might have them come back into the laboratory and drink lemonade with Splenda, and you have them do the same task both times. You might have some people start with the sugar condition and some people start with the Splenda condition and then swap. But either way, you have people do both conditions, and so you only need 30 participants in your research study. Now, the t-statistic for repeated measures design research is structurally similar to the other t-statistics that we've been working with. It's actually virtually identical to the single sample t-test that we did 2 modules ago. This, however, is based on difference scores that are indicated with a D, rather than raw scores, which we indicated before with an X. So a difference score is equal to x2 minus x1. You remember I showed you that on the very first slide where I showed that you might have people in the two conditions, and you take the second score minus the first score. So the post-test minus the pre-test. Score 2 minus score 1. If you had person A, B, C, and D, in this research situation, we might give them some kind of medication. It might be for, I don't know, maybe we need to bring their midichlorians down or something like that. So we give them a measure before the medications, and we see how high their midichlorians are, and then after the medications, and we see how high their midichlorians are then, and we figure out the difference. And well, if this medication was designed to bring them down, it did a terrible job because it raised most of them up. But anyway, the point here is that before medications and after medications are the original scores. We've got x2 and x1, so you'd take after x2, you'd subtract from it x1, and you'd get the difference score. And you need to compute the mean difference. So that is the sum of all the difference scores. If you add them all up here, that'd be the sum of the difference scores, or 64, and then you divide it by how many scores there are. In this case, there's just 4 different scores, so you divide it by 4, and you get 16. That's the mean difference score. Just take the mean of those scores. The hypotheses for a related samples t-test look like this. We usually, if we're doing a two-tailed, non-directional hypothesis test, we start with the null and we say the null hypothesis is that the mean difference is nothing. There is no difference between the two conditions because the treatment did nothing. So after meds, it would be the same as before meds. The alternative hypothesis is that the treatment did make some difference, and so the mean difference between the two conditions would be something other than 0. It might be higher or lower, but it's not going to be 0 because it made a difference. What this looks like is we have a population on the left which represents all the distributions, it represents the distribution of all the different scores that center around 0. The one on the right is an example of all the possible different scores if the treatment really worked and it centers something higher than 0. So here, if we took the two populations and we computed different score after different score after different score between the two groups, and then we plotted all the possible differences, and if the null was true, we would expect on average for there to be no difference. Sometimes we would find a difference, of course. It might be, a couple of points higher or a couple of points lower, but they shouldn't be very big because there isn't really a difference. The treatment didn't work, so there is no difference, so most of the scores are around 0. That said, if the treatment actually did something, then we would expect, and I just made up positive 5 here as the value that these are going to be centered around, but it doesn't matter what it is. It could just be whatever the size of the treatment effect is, however much it improved people's scores. But in this situation, I'm just making up that it might be about 5 points higher. And if you took the second score minus the first score over and over and over again, you're going to find that on average, they're going to center around 5 points higher the second time around than the scores that were measured the first time around. Sometimes they'll be a little higher than that, 6 or 7 points, sometimes a little lower, 4 or 3. But usually you're not going to find no difference because there really was a treatment effect. The treatment really worked, and so you'd expect it to center around something higher than 0. And it's the difference between these two hypothetical possibilities that we're trying to decide. Is there really no difference, or is there really a difference, something other than 0? The t-statistic for related samples t-tests are computed using these 4 formulas. These are not actually indicated in your formula sheet because they're exactly the same as the single sample t-test. They just have all these D's written in because this is saying it's the mean difference minus the population mean difference and the standard error of the mean difference, and the standard error of the mean difference is the standard deviation of the differences, and the standard deviation of the differences is computed the same as the standard deviation of all the other things, SS over DF, square root of that, and then the sum of squares is just the sum of the different scores rather than the x scores. And you take over here the sum of the different scores rather than the x scores and square them. So you can see that all of these things are we just added in a bunch of d's to just as reminders to tell you you're not using the original scores, you're using the different scores. But if you're an astute student, and you know that you're doing this kind of repeated measures t-test, where you have the same people measured more than once, then you know that you're using the different scores, because I've just told you you're always going to compute the second score minus the first score and run your t-test on the D's, on those different scores. So you don't need these in your formula sheet because they're exactly the same as all the other formulas I've previously showed you, just with these little D reminders. Okay. Now let's go through an example. An example of the repeated measures t-test. Does swearing focus our attention on pain, thus increasing it, or does it distract us from the pain, thus decreasing it? Participants in one study placed their hand in ice water as long as they could stand it. Eventually it's going to be too painful and they have to take it out. But while it's in there, half of them repeated their favorite swear word and half of them repeated a neutral word. Then they switched hands to the other and did the test again with the other condition. So if they started with the swear word, then they used their other hand for a for a neutral word. And if they started with the neutral word, then they used their other hand for the swear word. So everyone's doing both conditions. This research scenario will allow us to see, do people have more pain from swearing or less pain from swearing? The data summary here is we've got these 9 participants, and each one has 2 scores, a neutral word and a swearing word score. So these are pain levels. This person had a pain level of 9. I guess probably it's, I would guess this is a measure of how long they could keep their hand in the cold water, rather than like an actual pain level, but these units don't really make sense for that. So anyway, it doesn't matter. This is some pain level of 9 with neutral word and lower pain when swearing. 8 is the pain level when participant B used a neutral word, and 7 was the pain level when they used a swearing word. So for every participant, you've got 2 conditions. We've got 9 participants, and we can compute the D, the difference score, for all 9 participants by taking the swearing minus the neutral, swearing minus the neutral, swearing minus the neutral, and you have the difference scores here. We can also square these different scores because we're going to need them in order to compute our sum of squares in just a minute. So the sum of the D's is negative 18, and the sum of the D squares is 68. If you compute the mean difference, that's taking the sum of all the D's and dividing it by 9. So negative 18 divided by 9 is negative 2. How do we interpret that? That means that on average, people were about 2 points lower pain when they swore than they were when they used a neutral word. 2 points lower on the pain scale when they used a swear word than the neutral word. We can also compute the sum of squares here, like I said, using the computational formula. This is not the definitional formula. So you can see here, this is just like the computational formula that you've got in your formula sheet, but instead of x's, we just have d's here as a reminder that we're using the different scores, not the original scores. So the sum of the d squared is here, 68. The sum of d is negative 18 squared divided by the n size here is 9. So 68 minus negative 18 squared over 9 equals 68 minus 36 equals 32. So our sum of squares is 32. And I'm going to plug that up in this upper right-hand corner as a reminder to us while we proceed through the rest of our statistical hypothesis testing. So our hypothesis test begins, as always, with the first step, which is state the hypotheses and select an alpha level. So you should remember here that the null hypothesis is, pause your video for a second if you need to, and maybe even write out what it is. The mean difference equals 0. And the alternative hypothesis is the mean difference is something other than 0. It's not equal to 0. Okay, now step 2. We locate the critical region, and we decide the alpha level. It's 0.05. For this example, we have an n of 9, so the t-statistic has a degrees of freedom of n minus 1, 8. Therefore, the critical value in the t-distribution table is, now please really do pause your video, go to your t-distribution table, that's B.2, and look up what the t value would be in this table. Okay, your critical t is plus or minus 2.306. So you mark the regions that separate out the lowest 2.5% and the highest 2.5%. In your table, that's indicated by 5% combined in the two tails. And you find negative 2.306 on the lower end, positive 2.306 on the upper end. Okay, we've got step 3 now. Calculate the t-statistic. Look in your table, in your formula sheet, to see what is the formula for standard deviation. Now remember, we've got the d-score here as a reminder for this particular module, but in your formula sheet, it's not going to say the little d. So look for the formula for the standard deviation. That's the square root of SS over DF. That equals, look up here, we've already computed our sum of squares on a previous slide, that's 32, and if you remember from our last slide, the degrees of freedom was 8, so 32 over 8, square root of that, 2. Now look in your formula sheet again to find the standard error of the mean difference. Remember, there's not going to be a d in your formula sheet, so just find the standard error of the mean, and remember that you're doing this on the difference scores, not the original scores. Hopefully you found your formula was standard deviation over the square root of n. If you plug in these values, the standard deviation you just computed is 2, and the n is 9. So 2 over the square root of 9 is 2 over 3.667. Finally, we compute our t. Go to your formula sheet and figure out what would be the right formula for computing a t here. Hopefully you found that the formula was the mean minus the mu over the standard error of the mean. You'll notice that here in this PowerPoint we have these d's listed, but they're not in your formula sheet. So we take the mean of the different scores, which was up here -2. Remember, they're 2 points less pain if they swear, minus the mean of the difference scores in the population. Now, one thing we need to know about this is that just like in the independent samples t-test, this value right here will always be 0. This is always going to be 0 because our hypothesis is that in the population, according to the null, there shouldn't be a difference. If the null is true, then the difference scores will be no different, and this will always be 0. So you're comparing the mean difference that we obtained over the standard error of the mean that we expect to find just by chance if the null were true. So this is -2 minus 0. This is always going to be 0. -2 is our difference divided by the standard error of the mean, which we just computed. And we carry this through to -3 as our t-value. Just so that we remind ourselves what this means in practical terms, the -2 is how big a difference we actually found when we compared the swearing pain with the neutral word pain. They were 2 points less pain if they swore, and we would expect just by chance to find a difference of about 0.667. So we found a difference that was quite larger than that. How much larger? It was about 3 times bigger than we would expect to find just by chance. Now, is that greater than or less than the critical t we obtained before? Step 4 is to make a decision. Remember, we had this distribution we sketched out. We have our critical regions marked by the -2.306 and the positive 2.306. Our t we just got was -3, so where does that fall? As you see, it falls right about here at -3. So that falls in the critical region, and what do? Reject the null! So the t-value we obtained suggests that the null hypothesis is false and pain is really lower when you swear than if you don't. So, conceptually, we need to make a distinction here between two possibilities, and we have to decide which is more likely. This is the distribution of all the possible differences between the two scores if the null is true. So if swearing doesn't actually help at all, then we would expect for the people's pain score when they swear and the people's pain score when they're neutral to be about the same, to have no difference. And if you took all the possible differences and you computed them, you'd find that most of them are 0 or a little higher than 0, a little lower than 0, but they center around 0 because there's no benefit to swearing. But every once in a while, you might find a difference between the people in your sample that ends up being much higher or much lower just by chance, even though the null hypothesis is true and swearing doesn't actually make a difference. That might happen from time to time, and this could be that time, but that will only happen every once in a while, like less than 1% of the time. And so if this were that time, we would just be really unfortunate. We'd be making the wrong decision here because we decided that we're really rejecting the null hypothesis. We think this is actually an unlikely scenario, but we could be wrong. And this could actually be just that 1% of time where we got an extreme score just by chance. But is that more likely, or this? That this score right here is actually part of the sampling distribution of all the possible differences if the null were false and pain actually were benefited by swearing. So that people who swear have less pain, centering around something like -3, maybe sometimes it's 4 points less or 2 points less, but something around -3. And this mean right here actually came from the true sampling distribution of if the null were false, and these were all the different scores under that scenario. So we have to decide, does this score right here that we just obtained of -3, does it seem like it's actually part of this distribution or actually part of this distribution? It seems like it's probably part of this distribution. Now, it could be part of this one. It could be, but probably not. And so that's the reason why we reject the null hypothesis and we say probably the treatment actually worked and the null really is false. We don't know for sure, but we think that. When we run that hypothesis test, it doesn't tell us anything about the magnitude of our effect. Is 2 points of pain a lot less, or is it just like a tiny bit less? We can figure that out by running the estimated Cohen's d. Now, the estimated Cohen's d formula is the mean difference that we actually obtained minus the mean difference that we expect there to be just if the null were true. Again, this is always going to be 0, always 0, always 0. In your formula sheet, you'll find that Cohen's d is listed, but not for this particular chapter. In particular, it's not going to list your d's right here, and so you just have to go to your formula sheet, and I strongly recommend you do that right now. Look at your formula sheet, see that Cohen's d's formula is there, and it says the mean of the sample minus the mean of the population. And you need to remember that whenever you're running a dependent samples or related measures t-test, that the mean difference you hypothesize there being is always going to be 0. So you compare the mean difference that you actually got divided by the standard deviation, how big of a difference you, what you're doing here is comparing the size of the difference you found in terms of standard deviation units. So to compute our d, we take the mean difference, that's -2, and we divide it by the standard deviation, that is 2. And so we have -2 divided by 2, which equals -1. Now, whenever you find a negative Cohen's d, you ignore the minus sign and just report the Cohen's d as a positive value. So how would I interpret this? We've got a value of 1 here. We have to interpret it in terms of its size and its meaning. please take a moment, pause your video, and tell me how big of a D is this? This Cohen's D of 1. How big is it? Small, medium, or large? And what does it mean? How do we interpret this in terms of what it really means? Hopefully, you said that this was a large Cohen's D because remember the outline is 0.2, 0.5, 0.8. And a Cohen's D of 1 is larger than 0.8, so we would say this is a large Cohen's D. In terms of what it really means, hopefully you said this means that when people swear, they have pain scores that are 1 standard deviation less than if they don't swear. We also need to be able to compute an effect size in terms of the percentage of variability that's accounted for. So that's abbreviated R squared, and the formula that you use in your formula sheet is the same here. We square our t and put it over the squared t plus the degrees of freedom. You remember we had 9 participants in this situation, so you use the degrees of freedom 8, and our t here is -3. So you square -3 and put it over the square of -3 plus 8. If you carry that through, you've got 9 over 17. And if you divide that out, you've got 0.529. So your R squared is 0.529. We need to interpret this in terms of its size and meaning. Please pause your video and try to do both of those. Hopefully you said that the size was large. Remember the R squared table of size values is different than the table of Cohen's D values. So this is 0.01, 0.09, and 0.25 as small, medium, and large. This is 53%, 0.529. That's much higher than the cutoff for large, which is 0.25. And so we would say this is a large effect size. Now, in terms of what it really means, we would say 53% of the variability in this situation is accounted for by whether people swore or not. 53% of the variability in this study, in this data set, is accounted for by the independent variable, which is whether they swore or not. We finally need to compute our confidence interval. This is the same formula we have in our formula sheet, but again, we are going to just write these little D's as reminders in the slides, but it's not in your formula sheet. Just remember that you need to use the different scores rather than the original scores. So we're trying to figure out what is the actual difference in the population. That imaginary population, that hypothesized population, what is the real difference? We think it's about -2. We think people will feel 2 points less pain if they swear. But we don't know if it's exactly 2, or if it's maybe like 3 points less, or 1 point less, or something like that. But we think it's about 2, and we want to know what is it really? What's the range of values? So we think it's -2, but we think it might be plus or minus something. And we need to figure out what that plus or minus something is. What is this t? Remember, is this the obtained t or the critical t? This alpha next to it indicates that that's the critical t. So this is associated with the alpha level that you want to use when you compute your 95% confidence intervals. So you don't use your obtained t, it's the critical t. And the standard error of the mean difference is computed over here. You've got 0.667. So if you put all those things into the formula, you will carry this out to be, we think it's about 2 points less, but it might be plus or minus about 1.5. So if you carry this through on the upper side and the lower side, you should see that our confidence interval ranges from, pause your video and carry this through, you should find that it ranges from -3.5 up to -0.46. But notice that both of these are negative, so the range does not include 0, which means this is a statistically significant finding. In the literature, we would always write up a sentence to describe what we found. It might say something like this. Changing from a neutral word to a swear word reduced the perceived level of pain by an average of 2 points with a standard deviation of 2. The treatment effect was statistically significant, comma, t with degrees of freedom in parentheses equals -3, comma, p less than 0.05, comma, r squared equals 0.529. You might also list d there instead if you prefer, and then comma, 95% confidence interval ranges from -0.462 to -3.538. Those two values are separated by a comma and they appear in brackets. So that's how you write up a sentence in APA format for the literature. But we don't always use a two-tailed non-directional test. Sometimes we might have a specific hypothesis for related samples designs, in which case we would write out our null and alternative hypotheses slightly differently. So, as always, when you're doing the directional kinds of tests, it's easier to start with the alternative hypothesis because it's more intuitive. So we would say the alternative hypothesis is that the mean difference is greater than 0. And we would say that it's greater than 0 if we thought the treatment was improving scores, or we might say it was less than 0 if we thought that it was making the scores lower. But then whatever we say here, we just make the null hypothesis say the opposite of that. So the mean difference that we're hypothesizing is less than or equal to 0 if we said here that it would be greater. Using the same example as before, this example of swearing or not swearing while having one's hand in ice water, let's walk through a directional test. Step 1 is to state the hypotheses and select an alpha level. If we give you alpha of 0.01 and we're doing a one-tailed test, then we would start with the with the alternative hypothesis here. And what would you write that out as? Pause your video and write on a piece of paper what you think this should say. So the mean difference is less than 0. Why? Because the pain decreases when you're swearing, and the null hypothesis is the opposite of that, so the mean difference is everything greater than or equal to 0. In other words, pain does not decrease with swearing. Step 2 is to locate the critical region. For this example, we had an n of 9. Remember, we had these 9 people up here. So the t statistic has a degrees of freedom of 8, same as before. Therefore, the critical value in the t distribution table is, please pause your video and go figure it out. You should have found that it was -2.896. It's only on the negative side because we're using a one-tailed test, and we think that the pain will reduce people's pain. Step 3 is to calculate the t statistic. We've already done this. It's the same as before, so our t was -3. We plot that in the critical region. Remember, our critical t was 2.896, so that's the boundary right there, and -3 falls within the critical region, somewhere around there. We have to make a decision. Do we reject the null or fail to reject it? We reject the null because the t value we obtained falls in the tail of the distribution, less than 1%, p less than 0.01. And then we write it up. Swearing, compared to repeating a neutral word, significantly decreased the pain ratings, comma, t equals -3, comma, p less than 0.01, comma, one-tailed. And we always specify one-tailed if we've done a directional test. Now, these are some things that you need to take into consideration when you're choosing to do either a related samples t-test or an independent samples t-test. Remember, related samples are what we're doing in this module, where we've got two groups that are related to each other, or one group that is related to themselves, and we're comparing the differences between them. Versus the independent samples, which were two completely different groups, not matched on any characteristics. Usually they're randomly assigned, but they're independent of each other. There are certain advantages of repeated measures designs. That's what we're talking about in this module. They require fewer subjects. You can do it with less people. You're able to study changes over time, so you can track what happens if you have the same people before and after treatment. It reduces or eliminates the influence of individual differences, which is what I was talking about before, where you're comparing the same people against themselves, and so of course you're going to be reducing that error variance because of individual differences across the groups. And finally, it includes substantially less variability in the scores, and so it's actually quite a bit easier to come away with a significant t-score. There are some disadvantages, though. Factors besides the treatment may be causing subject score to change during the time between measurements. If, for instance, you do a pre-post design, then you have the treatment in the middle of the two scores. The treatment might be the reason for an increase or a decrease. However, some other things might be happening in the lives of the people who are undergoing treatment. And if something else happens in the middle, between the pre and post, that could also have influenced the outcome of your design, and so you're less able to determine causality when you use a pre-post design. Also, participation in some first treatment may influence scores in the second treatment. These are called order effects. You can counter this by using what's called counterbalancing, so that's a way to control for the time-related order effects, but these order effects can be what's considered a confounding variable. If you, for instance, think back to that example that we used before about drinking lemonade with sugar or lemonade with Splenda, if you had people drink the sugar lemonade first, and then you had them drink the other lemonade with Splenda just like 5 minutes later, then the sugar lemonade would influence their brain, and you couldn't detect what's going on from the Splenda lemonade thereafter, because the impact of the sugar has already wrought its effect on the brain. They've already got the additional willpower because of the glucose in their brain that they needed from the sugar lemonade, and so if you didn't randomize the order, and if you did do them too close in time, then you would find that both conditions appeared to give the same benefit of glucose to the brain, helping self-control, but even though the second condition didn't actually do that. So if you counterbalance, that can help to control for that kind of effect, where half the people might take the Splenda lemonade first and then do the sugar lemonade, and you would be able to discern in that situation that the group who did the Splenda lemonade first actually didn't show any benefit to their willpower from the Splenda lemonade, but they did from the sugar lemonade. In any case, you want to try and be careful about these order effects, that they're not unduly influencing the effects of the treatment just based on which one came first, which treatment condition you gave first. I also want to remind you about a couple of factors that influence hypothesis test outcomes. These are things that we've talked about in the last few modules, but I want to rehash them just again to get it in your memory a little better. Effect size is impacted by various decisions that you might make. If you have a larger mean difference, then there's a larger t. A larger mean difference, that means the scores are farther apart in the two conditions. Then you're likely to have a larger t. The sample size can also influence the size of your t. If you have a larger sample size, that means a larger t. Remember why? Because if you have larger sample sizes, your sampling distributions are narrower, and it's easier to tell the difference between two sampling distributions that are narrow than two sampling distributions that are wide and overlapping. Finally, the sample variance can make a difference in the size of your t. If you have larger variance, then you have a smaller t. Remember, that's because the variability is overlapping, or it makes the data messier, and so if you have more random variance, larger error variance, then the sample scores are overlapping too much to be able to tell whether there's a real difference. So that will yield a smaller t. The t-test also comes with certain assumptions, mathematical assumptions, that need to be true in order for us to trust the outcomes of our t-statistic. The first one is that observations within each treatment condition must be independent. This is unique compared to the other ones, because always before I've said the observations need to be independent, but here we're saying they need to be independent within each treatment. Why do I say that? Because obviously a person is related to him or herself. If you're measuring me twice, I'm the same person, so I'm going to be related to myself. But what this means is the different scores have to be independent of each other. You don't want to have, like, the people you've recruited in the study to be related to each other in some fashion, either genetically or in the same neighborhood or in the same major, or to all be selected based on some criteria that wasn't actually part of your study. Okay, population distribution of different scores also should be normally distributed, though it's okay if we violate this assumption as long as the sample size is sufficiently large. If it's small, then it might be a serious concern, but if you have at least 30 in your sample size, then usually you can ignore this because the sampling distribution will be normally shaped even if the population wasn't. Okay, before we end the module, please take a moment and work through this practice exercise. A marketer is testing whether a TV advertisement can change customers' opinion about a product by measuring attitudes in a sample of 9 focus group participants before and after they watched the commercial. For this sample, attitude scores increased after the treatment by an average of 1.9 points, and the variability was a sum of squares of 200. So, are the data sufficient to conclude that the ad had a significant effect on their opinions? Use a two-tailed test with an alpha of 0.05. Then compute the effect size for the ad using both Cohen's d and r squared, and compute the confidence interval for the population mean difference, and then write a sentence as if you were submitting these findings in a formal report to the executive leadership of the company. Use the same APA format that we've been talking about before. Pause your video, work through it, and then I'll show you the answers. Alright, you should have found that the critical t was plus or minus 2.306. We had a two-tailed test because we were just asking if there was any difference. And so you would find that the tail on the upper boundary and the tail on the lower boundary would be the same. Our obtained t was 1.14, and because that was within the middle 95%, then you would not be able to reject the null hypothesis. And you can see here your d and r squared and a 95% confidence interval, but your sentence should say something like, our advertisement did not significantly affect customers' opinions, comma, t equals 1.14, comma, p greater than 0.05. Remember, it's in the greater portion of the distribution, the larger 95% in the middle, greater than 0.05. Then a comma, r squared, or d, whichever you prefer, comma, 95% confidence interval, period. There you have it. That's our third and final type of t-test. Hopefully it felt very familiar to you by this point, having worked through many examples. But when you do your homework, you will find that you're concretizing the material that we've learned over these 3 modules, and hopefully well equipped now to understand what the t-statistic is representing and how to use it in real life.